Okay, recording, meeting controls. Okay, so good morning and happy, what's today? Wednesday. Today I'll be talking a little bit about information theory, specifically entropy, which is a tool used for our next machine learning model, namely decision trees. And decision trees are an important category of models, so-called interpretable models, which unlike regression and PLA, it's really hard to interpret what these weights mean. But for a decision tree, when you visualize it, it tells you precisely how it arrived upon the particular classification that it produced. Okay, let's see. Yeah, all right. So hopefully I'll remember everything. I'm probably the worst example of sleep deficit that you'll probably find. So I'm running on 5 hours of sleep for various reasons. Um, so if there's something that doesn't make sense, please make sure to, or don't hesitate to ask for clarification. Okay, all right. So before we begin, some administrative bits. The reading has changed. I've added a PDF, the PDF from Learning from Data on regression, which is the training treatment that we talked about on, was it Friday? Yeah, I think it was Friday. On Friday, this particular PDF is for decision trees, and it's written from one of the more famous machine learning books, or it's excerpted, written by Tom Mitchell, who's a pioneer in the field. He's also my academic grandfather. He was my advisor's advisor um, at Rutgers and then Carnegie Mellon. So that being the case, if you're one who likes the reading, the bits modality versus just how we talk about it in class, I always like to give you that option. Granted, it's not the only treatment for decision trees. Decision trees are very well known these days, and you can find online many other sources that talk about them. So if you're thinking like Gromit here, what more reading? I use it as a benchmark to provide you that modality if that's a modality that's more desirable to you. After today, there are two more class meetings. You're almost towards the end. Nobody will be more enthusiastic about the end of classes than I will, and certainly you probably will too. Um, Hopefully, it's been a good semester so far. And what lies ahead is we'll look at ensemble methods on Friday, and then next week, Monday, either talk about how to make an effective presentation or maybe look at feature selection. And so, course evaluations period is open, and I highly encourage you to submit an evaluation for my class, for all your classes. Please invest, and I use that word invest, the few minutes it takes to do that. Tell us what you learned, whether you know, learned enough, too much, or if you would have liked to learn more. The class evaluations Course evaluations are completely anonymous. They get locked until after grades have been submitted to the registrar. And so, you're encouraged to be as forthright as you would like to. Do this for all of your classes. I know in my class, I take evaluations and feedback from students, and I reflect that in the next offering. And so the offering that you have this semester is somewhat different from this past fall's version of it, which I taught directly as a result of the evaluations. And so we covered some other material that is not in this version of the class. So we could spend more time on some of the statistical concerns. Okay, project number 6, the workshop is due Thursday evening. I could possibly extend it into Friday. I'm going to be releasing the final project sometime today. Actually, my wife is traveling to visit my in-laws or her parents today, actually. So it's just my daughter and me. So things are taking longer than they otherwise would since it's just me for the next week and a half. But that being the case, please look out for the final project. It directly uses what you've exercised in Project 6, and the purpose of it was to get you practiced with using the various machine learning APIs that we've discussed. Okay. Any questions? Yes. Mhm. Yes. Over the next 6 days, I will be releasing a tranche of graded material. These are mostly projects as well as written exam number 2. And so I will know more on Saturday, and you'll know more on Saturday. Okay. Any other questions? Now, it's funny. People often, this course includes the designation of principles of practice, and people are often very nervous because of the mathematical concerns that we talk about. And I really do try to give everyone an opportunity to demonstrate what he or she understands mastery-wise by, choosing a method and applying that and demonstrating that you can extract information in the ways that we talked about. And so there are many different ways to do it. And, I acknowledge, and this is some feedback I got before, that it presents some students with discomfort because you're not used to that kind of thing, right? And so I really enterprise in the design of my classes to leave you with tools to be able to make those decisions that are open-ended, particularly for the types of data sets you would encounter in the real world where things are very messy, right? And so hopefully I've been able to do that. And a lot of times people are nervous about how am I going to do? How am I going to do? That as long as anybody is, coming to class, engaging, practicing, doing the things that they're supposed to do, sort of the student side of this academic contract, most of the times students do quite well, right? And often when students kind of, flub a little bit, it's when things are missed, like not handed in, as well as not following instructions and not answering the questions. And unfortunately, in those cases, and that's not your situation, or I'm not going to mention any particular person, but in those situations, there's no other alternative I have but to not, score 0 points and things like that. Okay. So please don't worry. I mean, yes, you're students. I remember being in your position and back in the Stone Age and stressing out about, grades because it's important, right? I get that. But as long as you're doing all the things you're being asked to do, usually it works out fairly well. Okay. All right. Contrary to what some might believe, I'm not out to get you, right? I really do want to pull you through from being a student to a data scientist in a sense, whether you do so willingly or kicking and screaming in some cases. But I do get those emails after the fact about, oh my gosh, I was able to use the stuff from class directly, or I talked about the projects and got an internship and stuff like that. Okay. All righty. I'm very proud of that aspect. All right. Any other questions? No? And so the final exam period is May 5th. So I don't choose that time, but thankfully for the first time in 2 years, I've gotten something that wasn't at 8 a.m. So I'm excited about that. It's going to be Friday, which is May 5th, from 10:30 a.m. to 12:30 p.m. And I'll be talking about the details of the final project on Friday after I release it sometime, probably this afternoon or this evening. Okay. Any questions? No? All right. So where we last left off, and I'm not going to spend a lot of time recapping since we used the regression and the APIs in the workshop, and we talked about it on Monday, but we talked about regression, and with this, certain aspect in our anatomy of a learner changed. The label by this unknown target function, it changed to real valued, and that impacts the labels that you have on the training example. They're real valued. And so we talked about this idea of real valued labels, but when you select your data or you're given your data, this real valued label can be an arbitrary feature. And so if you have some feature set, in this case in 2 dimensions, the first feature along the horizontal axis could be your real valued label associated with each data point, or the second feature along the vertical axis in this diagram could be your label. And so what the ask is, when you use regression, oftentimes you're trying to find some functional relationships among D minus 1 many features, to try to predict or construct a function that will give you that dth feature. So one feature as a function of all of the other features. Now, it doesn't have to be all of them. It could be one feature as a function of two, a function of three of them, a function of 100 of them. It doesn't matter. It's how you define your regression model. Many questions? No? And so we talked about what a so-called 1D regression is, or 2D regression, and the dimensionality, and this is very careful terminology here, the dimensionality of the regression model is different from the dimensionality of the feature space. And so here on the left, we have a three-dimensional feature space. We have x1, x2, and then we have this horizontal axis going up and down, our y-axis. You could call it your x3 axis if you wanted to be more formal. And it's called a 2D regression model, a plane, because the arity or the count of the parameters for that linear function is 2. So we're saying y is a function of x1 and x2 features for each one of the data points in your data set. Does that make sense? Or jar your memories? Okay. And so we talked about this idea of a best fit linear model. On the plane, it's called a line. In R3, three-dimensional feature space, it's a plane. But in arbitrary dimensions, it's called a hyperplane. So a hyperplane, if you look at the literature, is nothing more than a d-dimensional linear model. Okay. Any questions? No? And so we talked about this idea of the residual, the difference between the output of the linear model and the real valued output assigned by the unknown target function. And we use a squared error loss function because we care about the distance and not the magnitude. And so we expressed our so-called in-sample error, that difference between our predictor, our hyperplane, and the ground truth labels, real valued, over the entire in-sample data points are in-sample. And so we use tools from linear algebra. In particular, we were concerned with inversion of a matrix because we needed that to solve for this in-sample error. Okay, any questions? No? Jar your memory? And I strongly recommend that if you're interested in applying your craft in data science for a career, I strongly recommend that you take a linear algebra course because you're going to have to traffic in multivariate or vector valued quantities in the real world. Okay. And so we took our data and we put it in a row matrix to form what we called our design matrix. And this is just a matrix containing all of your data. Okay, so with that, we formulated an equivalent linear algebraic expression for in-sample error, and then we enterprise to find the weight vectors values that minimize this in-sample error. And so we did that by taking the derivative, and in multi-dimensions, the derivative is called the gradient, and setting it equal to 0, the derivative with respect to our weight vector W. And so we did that, and we ended up coming up with an expression we call the pseudo-inverse, and I wish the screen or that projector was kind of tipped up a little bit, so you'd see the bottom. And the pseudo-inverse is the solution for finding that set of weights, i.e. that hyperplane, that linear model in d dimensions, that is the best fit line. And that's the result of running your algorithm, so to speak. Now, with this, we changed the learning algorithm. And you might be thinking, gosh, well, did you really change the learning algorithm? All you did was solve for the pseudo-inverse. Well, the implementation of the pseudo-inverse is your learning algorithm. It's finding the W, the hyperplane in d dimensions, that best fits the data. And so whether you have something that's algorithmic, following a sequence of steps that eventually halts, or you implement some closed form mathematical solution, both of those are equally well valid learning algorithms. Okay, any questions? No? Questions? Jar your memory? Okay. So let's jump right in to some information theory. So if we think about the word information, everyone kind of has opinions about what information is. So let me throw that question out to all of you. What is information? Ever thought about that? What is information? Well, you extracted information, right? But what is this information? No? How about Ryan in the back? I know everyone's name, Alexander. Ryan, Sky, Claire, Tanner. See, in my mind, I was saying the wrong thing. Cecilia, Taylor, Ashley, Sophia, right? Get it wrong once and I'll remember it. The other Ryan, um, Shafi, and I remember you from Slack. Zuo. Um, how, Hawa. Okay. Yes. All right. So, Ryan, what is information? Try to exchange to obtain knowledge. Okay. How about Cecilia? What do you think? You agree with Ryan? Yeah. But does information change depending on how you might need something, might use it? Does information change? Uh-huh. Uh-huh. Okay. Based on the manipulations. Okay. How about Sophia? What do you think about information? I wish I could do this at the beginning of the semester, but I'm horrible remembering names. What do you think about information? Based on the transformations, okay? Hmm. And over time, okay. Why does it change over time? How about Shafi? Why does it change over time? What do you think? Get your sort of visceral, everyone's visceral understanding. Hmm. Okay. Perspective also changes. So it depends on what you need, right? What's important or the stuff you need can change depending on sort of what you want to ask from your data, right? Okay. All very good answers. So I'm going to present to you an image. And this image, let me ask you, can you see anything in this image? Anyone? You see black and white? Does any kind of pattern kind of emerge mysteriously? No? It was a trick question. Okay. There's no quote unquote information in this. It's just a randomized pattern. And in the early days of TV, when there was no station on the air, perish the thought, TV didn't get broadcast 24 hours a day. After the station signed off, there would just be this test signal, which was just um, normal or Gaussian noise. And this is what it looked like. Sometimes they call it snow, right? But it's a test pattern because they wanted to put something over the airwaves. So they didn't have any information. They just had this stuff that was different from information. Okay, well, there's no notion of structure there. And we haven't talked about what structure means. And structure kind of gets to this idea of knowledge, of, the result of these transformations. Because every time you apply a transformation on your data set, you're throwing away the stuff you don't want, right? And you're keeping those things you do want. But the things that you do want don't occur randomly. Where random, I mean the rigorous definition, all outcomes equally likely. It's something different from random, biased. So let's take a look at a different photo. And these two photos are not related to one another, I promise you. So, not a trick question this time. What do you see there? Just a farm, okay? You see a tree, you see some crops there, you see a fence, you see a road. Now, what makes this tree a tree is that the color and the position relative, the geometry among all the points, edges, and lines that form this tree and curves, they're not random. There's something different from random. They're very specific. There's structure there. It's not an arbitrary choice of what comes next to what else. So this idea of structure is precisely what we'll talk about and measure computationally when we talk about this idea of information. Does that make sense? Okay. And so when we look at information, information is sort of the dual, kind of the opposite of disorder. Disorder talks about this notion of randomness, that the wider the selection of values that you get for some observation, the more disorderly it is, the more messy it is. So if some observation, for example, takes on some values, and like we know, you want to enumerate our sample space omega, and to enumerate it, you need to count it, you need to number it. So let's imagine we had a system and we make an observation of that system. So we have a random variable, and we find that there are 65,536 different values that this observation can take on. Well, if we wanted to count these different observations, these values for the system, we're going to need 16 bits in order to do that. So this idea of description requires a representation. And if we're going to count these values, a large number, we need 16 bits computationally in order to do that. Does that make sense? So let's say you have a different system, and in this different system, you make an observation, but this system traffics in only 256 different values this observation can take on. So to count 256 values, you label the first one 0, then 1, then 2, and you'll need 8 bits in order to represent the observations possible or the size of the sample space omega for this particular system. Now we'll notice that 256 is a lot smaller than 65536. And so this notion of how numerous the set of values something can take on, how wiggly it is, if you want to call it that, you can use this idea of representation, the bit width, as a proxy for the numeracy or the size of our sample space. Does that make sense? All right. So using this idea, let's go forward and imagine then if we took our observations of different values and we computed a histogram. We know now that a random system treats each one of these outcomes as equally likely, and it assigns equal probability mass. And therefore, we get something that looks like this. Now, it might be a little bit different here or there in some places, but if you had enough examples, this particular distribution is going to be uniform. It's going to be straight across, equal probability mass for all of the different k many observations. Does that make sense? Okay. And so this idea of higher disorder corresponds to there being many more alternatives, and we can use the bit representation, the bit width needed in order to count them as a way of measuring this idea of these wide range of alternatives. Because if we're going to look at something like dispersion with the variance, if we have probability mass going across in one direction and the other direction across our sample space, all of the things or values along the horizontal axis, our variance is going to be large if we have probability mass that's very, very broadly spread out. Does that make sense? Any questions? No? All right. And so let's take a look at this system. Now, this system puts most of its probability mass in a narrower range of values. And so here, there are fewer alternatives. So this is more like that 8-bit example, where the former, this uniform distribution over the observations, is more like that 16-bit example. And so this idea of lower disorder is this notion of information. There's structure to it. It's not an arbitrary choice. It's a particular choice. Does that make sense? Of the values that you observe. And so lower disorder means more information because now you're making an informed choice. It's not arbitrary what values show up or relationships between points and images. It's a particular set of relationships. And if you were to take a distribution of relationships between pixels in the second picture, you'd get something that looks like this versus the first picture, you get something that looks like our uniform distribution. Does that make sense? Any questions? All right. And so information theory is a study or an area of mathematics, applied math, that talks about this idea of bit representation as a measurement of disorder. And if disorder is small, you have quote unquote more information. Does that make sense? Any questions? No? All right. And so Back in the early days of the telephone system, um, they were making the transition from so-called analog telephone systems to digital telephone systems. So instead of representing signals as voltages like 7.3 volts, 12.1 volts, they represented things or switched over to representing voice communications and later internet as binary values, where a plus one binary value is a 5 volts is the presence, it's the word I'm looking for, of 5 volts, and a binary zero or logic zero is represented as 0 volts. And so with the telephone system, it was pioneered this idea of the coding or the representation of signals as binary quantities was pioneered by Claude Shannon, and that's Claude Shannon, who was a scientist at Bell Labs. Now, back in the early days with the telephone system, Bell Labs, AT&T, I should say, was the only telephone company in the United States, right? That was it. Now, I remember when I was little, really, really little, when you subscribed to a telephone service, you paid a monthly fee, and it was to AT&T. And your telephone you didn't own, you rented it, and you rented it from AT&T. When you needed repairs done, you had to call AT&T, and everything was done through AT&T. It was a monopoly. And so some point in, I think it was 84, AT&T was broken up by the federal government under the, I forgot whatever law it was, the Sherman Act for anti-competitive practices. And so you could not buy your own telephone in like Best Buy or, Lechmere or whatever it was back then and go ahead and plug it in. No, you couldn't do that. Your phone had to come from AT&T, right? Now, it seems kind of weird by today's standards, but this breaking up of AT&T is sometimes called Ma Bell into the so-called baby bells. And when you have Pacific Bell in California, you have 9X, which used to be Atlantic Bell. Each one of these phone companies is the result of breaking apart this big behemoth, this monopoly, which was AT&T. Now, this is what a phone looked like when I was really little, like 4 to 6 years old, and it was a rotary phone. And with this rotary phone, this was an analog system, and you can still buy rotary phones on eBay. It's kind of pricey. They're considered collector's items, but these things will still work with your landline if you have a regular telephone line. And so with this, it was pure analog. And when you dialed on the phone in the early days, you didn't dial a phone number directly, right? You would dial a telephone operator, and this telephone operator would ask you what number you're trying to call. And this person would literally take a patch cord from one location representing your call and plug it in to make a physical electrical connection in another location. Now, in the early days, operators were mostly women. And in fact, in the earlier days of computing, earliest days, most programmers were primarily women. And so fast forward to today, women are underrepresented in computer science. And so many, including Clark, are trying to remedy that situation. But that being the case, you'd make an electrical connection. And over time, this making of an electrical connection was automated to a degree with an electromagnetic system called a phone relay switch. On the left-hand side, your left, that's a relay switch. And a relay switch has an electromagnet. And when you charge up the electromagnet, it pulls a piece of metal, and that makes a physical electrical connection. And so they automated this function of the operator, which meant now that when you dial your phone number, you didn't have to talk to an operator any longer. And so on the right-hand side, that's a picture of an early automated telephone switch. And you can see in these banks, these huge capacitors, and in there are electromagnets, and there are these high-speed relays that work at line speed, at the speed of electromagnetic energy going down the conductor that automated this switching function that used to be done by the operator. Okay, does that make sense? Any questions? It's fascinating to go back and look at some of the history. And so this is a modern telephone switch. Trying to pull the video up, and it looks like a server in a server room, which is exactly what modern switches are. And these modern switches are digital, right? They're computers, And now these computers make these switching decisions. But part of the problem is that voice signals are analog. Your voice is nothing more than a pressure wave. And when you speak into a microphone, your pressure wave for your voice going through the air is oscillating a piece of metal, which passes an electromagnet through a permanent magnet, and you get the induction of current in that coil of the electromagnet. And so by its nature, your voice is nothing more than a mixture of sine waves and cosine waves going down some copper wire. So in order to take that so-called analog signal and convert it into a digital signal, you need to take that level, frequency, and amount, amplitude of the sine and cosine waves for the frequencies of your voice. And you have to say, if it's between these values, this is the bit value that it corresponds to. So essentially, what you're doing is you're counting the different values that an observation can take on. And each of these observations is a different level of voltage corresponding to the amplitude of these sine waves and cosine waves from this microphone. Does that make sense? And so in the early days of the advent or the switching over to digital systems, preserving bandwidth was really, really important. They didn't want to use up a wider range of bit values because they didn't have that much bandwidth with which to transfer it. And remember, because it's voice communication, it needs to happen in real time. You can't say hello and then 10 seconds later, the person on the other end hears your hello. And so it was really important that this representation of these counts of values of these events for the signals going down the line was as compact as possible. You wanted to extract just the most important, quote unquote, information. Does that make sense? Okay. And so this study, pioneered by Claude Shannon, information theory, was a set of mathematical tools that you use to determine what is the optimal or the average or the best, if you will, representation based on signals. And here, the signal that we're going to talk about, we're going to treat that as a set of values that come in or arrive or observations that you make. And these values that you observe are going to be defined or governed by a probability. Does that make sense? All right. And so what we do in various ways in information theory is you measure the average number of bits used in order to communicate a signal. So we start out on the left-hand side with your voice signal. You have an encoder that does what's called quantizing. It chops up your range of values into discrete levels like bins of a histogram. And when it observes a value, it says, this is the value, and I can count all the different such values. Does that make sense? Any questions? No? All right. And so the idea then is you pass these values over a channel, and this channel is not perfect. You get interference. If you stretch a copper wire over a long distance, any electromagnetic field nearby is going to induce a current in that wire, and that's going to come across to you as extra information that you didn't originally transmit. And so on the other side, you take these values and you convert them back to frequencies, and the person on the other side hears that as your voice. But if you were to compare a recording of your voice in person to what someone hears on the other side of the phone, it's not going to be exactly the same. It's going to be a little bit different because this representation is not precise. Okay. And so Shannon created something that's called Shannon entropy, or just entropy. And what this entropy does, it takes the probability of the occurrence of some value or observation. That's our P of X. That's our P of X. And then it takes the log of this probability and it negates it. And so you can think of this Shannon entropy as the expected log probability. Now, when log is log base 2, not base E, this log will tell you the number of bits needed to represent something. Does that make sense? Okay. Now, this negative log probability or negative expected log probability is just an expectation, just like any other probabilistic average or expectation that we've been talking about. But this one uses log base 2 and computes the average number of bits weighted by the probability. All right, so this other quantity called the importance weight. Importance weight expresses what's called a likelihood ratio. It's the ratio between two likelihoods or probabilities. And let's imagine we had one signal P, which was your original signal coming into this channel, and you had another signal Q, which is the signal coming out of the channel that's corrupted by noise. Now, one of the things you might want to know is how similar are these things? And so the likelihood ratio is a way of expressing how much two different signals or probabilities agree on the amount of mass they place on a particular value. Does that make sense? Any questions? Because if it's the same probability, this ratio is going to be 1. And ideally, you want this to be as close to 1 as possible. And so if this likelihood ratio, or importance weight, as it's called, is close to 1, that means both signals P and Q, those two probabilities, agree on what the mass should be for that particular observation. If it's very small or very large, then that means these two signals do not agree. And so this importance weight gives a notion, if it's closer to 1, that this particular value is very important. Otherwise, it wouldn't be close to 1 because these two signals agree on it. And it's used in channel encoding to say what values are most relevant, i.e. not the noise, between the incoming signal to the channel and the outgoing signal from the channel. Does that make sense? All right. And so this importance weight talks about or measures a notion of shared information. It's what is important, and it's usually smaller than all of the values inbound and outbound to and from the channel because they agree on it. Because they agree on these values, i.e. the importance weight is close to 1, there must be something special about this set of values different from all the other values. Okay. Any questions? No? Excuse me. And so there's a notion of the distance, if you will, or the relative importance of information between two different signals or two different distributions. If you have two different systems, you want to know how different they are from one another. And so the so-called Kullback-Leibler divergence is a measure that uses this importance weight in its expectation to talk about the distance or the difference between two signals or the difference between two distributions. Does that make sense? Now, notation, it looks kind of funky, but that's the literal notation. We have the KL divergence between signals P and Q, and this is the expected, so it's a probabilistic average. And you'll notice here, it's Q relative to P. So Q relative to P, it's almost like saying, let me take distribution P. So let's imagine this was distribution P. And let's imagine this red was distribution Q. And it's almost like saying, let me take distribution Q and project it onto distribution P and to see where they share these information. Where is this likelihood ratio high, closer to 1, and therefore what's most important in terms of the values that are governed by these distributions. Does that make sense? And so here, the Kullback-Leibler divergence of P, I got that backwards, P relative to Q, is just this expected log likelihood ratio. So there's the log likelihood ratio, the expected log importance weight, and it's the expectation with respect to signal P. Does that make sense? Okay, so it's P relative to Q. And so you're taking Q and you're saying, where do I match with P? And that's this notion of a distance measure, how different or similar these two signals are. Okay, any questions? Yes. I'm hesitating because there's something specific called histogram intersection. That's a different measure, right? But because this works in distributions, it can be discrete or continuous. It's related, but it's entirely different from intersection. People try to have a data-intensive version, which is exactly something called histogram intersection. And you take the two, each bin for the histogram, and you say what is the common height among them, and then you add those up. And so I'm going to say no, it's not the same as the intersection, because the intersection doesn't traffic in probabilistic averages. Okay? All right. Any other questions? No? Make sense? All right. And so there's another type of entropy, this bit representation, and this is called the joint entropy. As I said before, that in the real world, you're going to traffic in vector valued instantiations. And so here, it's the expected log joint probability. Here's our log joint probability for two variables, and they're not independent. That's the assumption. And we're going to take the expectation, so we're going to weight that by the probability, the joint probability of every instantiation. And in this case, we have two variables, x and y. Does that make sense? Okay. And so what this is saying, what is the bit representation on average for this signal? And the thing that you're concerned about is the numeracy due to the coupling between these two variables, x and y. But in this case, you're talking about the bit representation for counting the values of this type of wiggliness, so to speak, numeracy in the observations, but it's between two things that are jointly occurring. Okay? All right. Any questions? And this is a visualization of a two-dimensional normal distribution. Here we have one variable x, we have another variable y, and along the horizontal axis, this is p of x, y. And so the mean mu would be a point on the plane, and mu is going to have an x value and a y value. The covariance is going to tell you, if you're looking from above, how elliptical or circular this distribution looks from up above. If you had something that's circular, looking from up above, it's going to look like concentric circles. If you had a covariance that was positive, it's going to look like an ellipse that's oriented in some fashion, the major and minor axis. Does that make sense? Okay. And so this joint entropy talks about the average number of bits or the disorder when your system is governed by a probability that's vector valued, that's different from the single variate case. All right. And so mutual information measures the following. With mutual information, you look at the signals, x and y, and what you're asking is how much of the disorder is due to disorder in the individual variables versus the covariance. And mutual information teases that out. Does that make sense? And so one of the things you'll see, it looks a lot like the joint entropy, except the log odds ratio is a little bit different, right? This log odds ratio, in the numerator, we have the joint probability with the assumption that they're not independent. And in the denominator, we have the product of the individual probabilities. And so in essence, what this is doing, it's saying, take the log odds ratio between two assumptions. In the numerator, that assumption says that they're jointly coupled, right? They have a covariance that's not zero. And in the denominator, that says relative to treating them as if they were perfectly independent. And so what this likelihood ratio is saying, do they agree, or how much do they agree under the independent assumption versus the non-independent assumption? And we take the log of that, and we take the weighted average, and this is our so-called mutual information. Does that make sense? Any questions? No? And so if we take this mutual information and we do some transformation, and log of p of x over the product of px times py, that's just log of pxy minus log of p of x plus log of p of y. Went off the screen. And so if we do the algebra, we get this equivalent expression. We have the entropy of individual variable x. We have the entropy of individual variable y. And we subtract from that the joint entropy, which we had 2 slides ago, which is the disorder due to the coupling of these variables, assuming that They are non-independent. And so essentially what's left is the disorder as represented by the average bit width due to the coupling of these variables. Does that make sense? All right. And so all of these things, if you deal with signal processing and as well as some aspects of mathematics, you're going to deal with information theory. And information theory, hopefully on Monday, is a great way for measuring the relationship or the coupling between variables when that relationship is nonlinear. Correlation is a perfectly fine measure, but correlation is limited only to linear relationships. Entropy, more specifically mutual information, will handle arbitrary nonlinear relationships. Does that make sense? And so one of the things we'll hopefully see on Monday is using mutual information to answer the question of which features are saying the same thing. Because if two features are very tightly coupled, you don't need both of them. So you can now eliminate a variable from your data set and thus reducing the dimensionality, which has desirable properties for your learning models. Any questions? Yes. Okay. For this term or just this, what this means? Okay. So imagine if you had a system, and let's imagine you had a let's think of an example. Let's imagine you had a die roll, right? And you had a coin flip. And let's imagine that 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Okay. So let's imagine you had two sets of die and you have an event, and that event was the outcome of a coin flip and the outcome of a die roll. So imagine if your coin flip comes up heads, you're going to use the regular die, the fair die, right? All sides equal probability. But if your coin flip came up tails, you're going to use a biased die. And let's imagine that it wasn't the case, that all the outcomes were the same. So let's imagine, outcome 1 through 5 were the same probability, but outcome 6 was different from the rest, right? And so with that, this joint probability talks about the probability of every outcome, heads, tails, 1 through 6, that you can have for each one of these cells, okay? Now, when you make this independence assumption, you're not making the assumption that there's some coupling, right? In this case, these are not independent because the outcome of one is going to change the outcome of the other. The outcome of the coin flip is going to change the outcome of the die roll. So in that case, we're basically treating these as if there is no coupling if we multiply the individual probabilities. Now, when I say P of X here, I don't mean marginalization, because marginalization said I acknowledge that they're coupled and I add values down the columns or across the row. That marginalization, when you use that procedure to arrive upon P of die or P of coin, that's saying, oh, they're coupled, right? But in this case, when I say P of X and P of Y, what I mean, here's my X, here's my Y, and I look at the values, X1, X2, X3, Y1, Y2, Y3, and I just treat this as a separate probability that has nothing to do with these values. And so that independence assumption, it's not correct. But what it does, it allows you to say, where does my dependent assumption match with my independent assumption? And that importance weight requires you to make a likelihood ratio between the product here, which is the independence assumption, which is not correct, and here, this is the dependent assumption. Does that make sense? Okay. Any other questions? No? All right. And so essentially what you're doing with mutual information, you have a bit representation that's useful for the joint probability for these two signals at the same time. And you're saying how much of it is due to the coupling versus the independence assumption. And so if we work out the math, you get entropy of one plus entropy of the other, and you subtract out the joint entropy. Okay. And so the KL divergence, this distance measure, is not symmetric. if we say the KL divergence of P relative to Q, so here's P relative to Q. I'll just do that to represent you're projecting Q onto P. And then this one, second version, is Q relative to P. You're projecting P onto Q, right? So they're not the same. KL is called a divergence and not a measure because a measure requires symmetry. You can reverse the order of the parameters, and it's the same result. That's not the case with KL divergence. Okay, well, how do you rectify this? The Jensen-Shannon divergence takes the two-way KL divergence, P upon Q and Q upon P, and it gives you a mixture of it. And with this Jensen-Shannon divergence, or JSD, it's like the KL divergence, but instead of doing P relative to Q, Q relative to P, it uses a so-called midpoint distribution. You take the probability from the perspective of the P distribution, the probability with respect to the Q distribution, and you take the average, right? Does that make sense? Okay. Now, this is the so-called symmetric smooth version of the KL divergence. And a contribution I made with my graduate student, Piyush, who's now at Army Research Lab, we changed Jensen-Shannon divergence because it has a flaw. And we basically took this midpoint, this arithmetic mean distribution, and replaced it with a family of means from the so-called Shishini means, which have desirable properties. And what it does, excuse me, is it takes the range of this KL divergence, of this Jensen-Shannon divergence, and it dilates it, it stretches it out. And one of the flaws with the Jensen-Shannon divergence is that if your two distributions are very close together, it doesn't do very well. But our Shishini-Jensen-Shannon divergence, CJSD, and I'm happy to share our paper with you if you're curious, it rectifies that situation. And we have rigorous proof as well as several domain applications where it plays out. Okay. A shameless plug. Excuse me. All right. And so this last one in sort of this repertoire of information theoretic quantities is a so-called Bregman divergence, or F entropy. And one of the problems with all the other ways of measuring information content in signals is that you don't get to define your functions. Suppose you have something like a heart signal, and you have a heart signal for certain segments of the population. Well, those can be modeled as distributions, but maybe you want the derivative, the change in heart signal, and not the raw measurement. So how do you insert your own function in a way that you can measure information? Now, this is called Bregman divergence, or so-called F entropy, where F is your function that you define. Now, this requires a so-called convex function. And a convex function is smooth and differentiable, so you can take the slope anywhere. And this definition of convex is as follows. Suppose you have your function, f of x, and let's say you have two intervals. You have a, some point over which f is defined, and you have b, okay? Well, this point, that's f of a, f evaluated at a. This point is f of b, f evaluated at b. Now let's imagine we had f of a and we have f of b, and let's draw a chord, which is just a line segment that pierces a curve, okay? So this is our chord over f, okay? Now, if we were to define an arbitrary point in this range, let's define what it would look like. Well, an arbitrary point in that interval between A and B is some mixture alpha times A plus 1 minus alpha times B, where alpha is on the closed interval between 0 and 1 on the real number line. Okay, because if you have alpha is equal to 1, well, you get exactly A. If you have alpha is equal to 0, you get exactly B. Anywhere between 0 and 1, it's an increment somewhere in this line segment between A and B inclusive. Does that make sense? All right. So now, if we evaluate f on alpha a plus 1 minus alpha b, if we evaluate this expression, this is nothing more than a point on the curve. That makes sense? It's f evaluated on any point between and inclusive of a and b. Now, for this chord, if we want to find a point on the chord is f is alpha times f of a plus 1 minus alpha times f of b, okay? Because f of a is here, f of b is there, and alpha, if it goes from 1 to 0, is along that line, along the chord. Does that make sense? So convex function is one that preserves, that preserves that relationship. And it says that the function is less than or equal to any point on the chord within that interval. Okay, does that make sense? All right. And so why did we talk about that? Well, you have to have a convex function, and you can prove convexity using that construct. As long as you have a convex function, there's a way to measure this idea of information content. All right. So let's take a look at how that works. Okay. Well, we have our function, and here we have w. That's our point here on the right. We have v, our point here on the left. Here we have f of w minus f of v. That difference is this distance. Okay. That distance, f of w minus f of v. Okay. Now, this other part, minus what? We have w minus v, that's this distance, w minus v, and then we have the gradient or the slope of f at point v. That's this line. And so what this Bregman divergence is telling you is what is the difference between the rise, change in value of the function, and that linear assumption starting at point v. Does that make sense? And so if we project that line out, assuming constant slope at point v, we get this difference. And that's the F entropy, or the so-called Bregman divergence. And it kind of makes sense. If your function is more wiggly, it changes and shifts very dramatically, more likely you're going to get a larger set of differences between the constant slope assumption and the actual distance of that function. Does that make sense? And so the more varied your function is, the higher this Bregman entropy is. The less varied your function is, something like this, does not increase very well. That difference is going to be much smaller. Does that make sense? And so it's an important aspect of entropy. And the reason why I spend time on that is because there are some signals where you want to be able to define your own transformation on it and still talk about this idea of information content. Does that make sense? All right. All right, so let's continue forward and let's get to decision trees. And decision trees uses information theory to search through the space of hypotheses to find that final best hypothesis that most closely agrees with the unknown target function. And so it's a way of learning target functions. And if we don't finish today, we'll pick up the balance on Friday. And so here we have our unknown target function. So this is the supervised learning problem. And it's out there labeling our input vector instantiations. And in this case, with a decision tree, it'll work with a binary decision problem like approve, deny. It'll also work with an arbitrary k-way decision problem directly. So our label set is discrete, and it can be of arbitrary size. And I have a Jupyter Notebook example where we take our data set for the mortgage approval problem, and we partition it into 4 groups, and I'll show you the decision tree for a grouping of 2, as well as a grouping of 4. Okay, and so the 2 algorithms, learning algorithms for decision tree, the first one was called ID3, called Iterative Deepening version 3. And then the improvement on that fixes up an issue with ID3 is called C4.5. And this was contributed, C4.5, by someone named Ross Quinlan, which is an interesting person because this person was never a professor um, uh, at a university and was not in a research lab, was just an individual who thought it'd be cool to just do some research and contributed some really nice work. And so the benefit, as I said at the outset, of our decision tree is that you can read off these models. Okay, so they can actually tell you why specifically someone was denied a mortgage and why specifically someone was approved a mortgage. And for certain domain applications, it's important to have interpretable models, especially when there's federal law behind it that says you're required to furnish reasons for certain decisions. Does that make sense? Any questions? And so let me make sure my mic is still on. Yep, still on. Because when I go to a certain part of the room, it drops coverage. All right. So we're going to start with a set of label instance pairs. And it's our vector instantiations, X. Each one has a ground truth label assigned by the target function. And in this, we're just going to assume we have our label set, K-many labels, and we call that L1 through LK. All right. And so what you do with a decision tree, it's called a tree because it has our tree structure, and this tree structure is a graph, and it starts with a so-called root node at the top, and then each root node has a set of so-called child nodes, and then eventually, if you traverse any path from root to through the children, you get to a last node in the tree, and that's called your leaf node. So in these trees, you can almost imagine taking our tree structure and kind of turning it upside down. It looks like a regular tree, but computer science, their trees are upside down. They grow downward. But that being the case, you take your instance when you're going to use your decision tree, your new data, and you start it down each one of these nodes. Now, each node consists of a statistical test. And if it passes the test, this data point traverses the left projection of child on the node. And if it, did I say fails? If it fails the test, you go down one branch. And if it passes the test, you go down the other branch. You can also choose a bunch of different tests for that same instance that has more than one alternative for its outcome. But for the theory, we're going to talk about the two-way outcome case, passing the test and failing the test, okay? And eventually, your new data point, if you traverse this tree, applying the test corresponding to each one of the nodes in the tree, eventually it comes to rest in a root node. And when it comes to rest in a root node, you're going to look at the majority class label with all of the training examples that have accumulated in that leaf node. And that's going to be the prediction for what the class label should be. Does that make sense? And so here we have our vector valued data. And for each one of our vector instantiations, we have a label, a value for that attribute. And so let's say if we had the first dimension on through the dth dimension, right? Each one of these attributes in our dimension A, it takes on a value across the data set. And so here we're going to use Xij to represent, hopefully I get this right, the jth, let's see if I get that right. For the jth attribute, what is the ith value? And so let's say we had, for example, years in residence, right, from our mortgage approval problem. If we go down through each one of our vector instantiations, looking at years in residence, that might be, for example, you might have years in residence of 15, another one that was 7.5, another one that was 3, another one that was 2, 1, 2, and so forth. And so what we're looking at here is all of the different values that a particular variable can take on across the data set. Does that make sense? Yeah? All right. And so when we do that, we're going to encode in our nodes in the tree a question. And that question is, for that particular variable, like years in residence, was it greater than a particular value among all the values that it can take on, or was it less than equal to that value? So that's a yes/no question. Does that make sense? All right. And so what we're going to do then is we're going to now find the set of questions. Is it less than a particular value for a certain attribute, or greater than or less than equal to? And that answer to the question based on that particular attribute is going to cause you to partition your data. So for some data points, it's going to pass that question. For some data points, it's going to fail that question. And the result of passing or failure means that you set aside those data points that pass and you set aside those that fail, and you measure the reduction in disorder, right? And so ultimately, what you're looking for is what set of nodes or questions or splits of the data points you can make that make the resulting subgroups when you partition as homogeneous as possible, i.e., more and more information. Does that make sense? Any questions? So we only have about 8 minutes left. Let me pop into the Jupyter Notebook and I'll revisit the Jupyter Notebook, but I just want to show you what these trees look like from an actual data set. And we'll just continue on with classification. I spent more time than I thought I would on entropy to kind of show you what an actual decision tree looks like, rather than just talking about the theory for now, since we have about 8 minutes left. So I'm going to bring up my Jupyter Notebook. Let me share screen, decision tree. All right. So let me see, bring that up. And so in this data set, I've done two clusterings. One is a clustering, the microphone is down. One is a clustering of our mortgage approval problem in its original partitioning. That's in two groups, approval or denial. I partition the data set based on the ground truth target function, the supervised learning problem. And so the red points in the point cloud are the denials, and the blue points in the point cloud are the approvals. So I go ahead and I take that binary decision problem and I do a train test split, setting aside 10% of our data randomized as the test set. And then with the remaining 90%, I train a decision tree. And so here I go into the tree API from scikit-learn. Let me see where it is. Scikit-learn, sklearn, the tree API. And I go ahead and I fit that decision tree using that 90% set aside for the training data. And so here, the criteria that I'm using is entropy. On Friday, we'll learn its gain ratio, right? Which we won't talk about today. So I train my decision tree, and then I go ahead and I fit it to the data, and I go ahead and I'm going to plot out what that tree looks like. And so here we have the first node, and it says my first feature, I have two features, the 0th feature and the first feature. If it's less than or equal to 15.568, if they pass, it goes down this left-hand edge to the child node. And if it fails, it goes down the other edge. And so this decision tree, once you get to the root, it's these are the classifications and the majority labels. Now, when you give a, this has been a long day so far. When you have a new example, if they say you were denied, you can say it's because your years in residence was less than 15.5, for example, or your annual salary was greater than 65,000 and change, right? And so this so-called interpretable model, it's a classifier, supervised learning problem, but after the fact, you can read out the model, and if someone was approved or denied, you can actually tell someone specifically what those thresholds were and be able to furnish that and in a letter of some sort to comply with federal law. Does that make sense? Okay. And so if we can do it, now let's compare the in-sample error with the out-of-sample error. Well, in-sample error, in, is 100%, out-of-sample is 100%. Okay. So let's do something more interesting. Let's cluster into 4 groupings, even though we know optimal by Davies-Bolden score is 2 groupings at this juncture. We're going to say, go ahead and partition our data into 4 groupings running Lloyd's algorithm. And we're going to plot this. So these are our 4 groupings. And you can almost imagine of the denials, you have the hard denials, those who are on the low side, of the denials and those who are on the high side of the denial. So you might use this type of information maybe to have special programs for those who were denied. You can sub-partition into other groupings. And so now we take these 4 groups as visualized, and we go ahead and we associate with them, after doing some summary statistics, some class labels. So we're going to have labels called group 1, class 1, class 2, class 3, class 4. And so now we're no longer doing approval or denial, where +1 is approval and -1 is denial. We're saying group 1, group 2, group 3, group 4, and the group number, we're calling out class labels. So in this case, our label set for the supervised learning problem is of size 4. And so that's a more difficult problem because to classify, because we've partitioned it into 4 groups. And so I go ahead and I construct a decision tree with that new version of the data set that I've assigned labels based on the 4-way clustering. So I go ahead and I do that, and I'll go ahead and let's print out what the decision tree looks like. And you can see that decision tree is a lot more complex because we have more class labels. And we're partitioning the data based on different criteria because it's a 4-way grouping. And so again, here, I'll blow that up. We have the root of the tree, and it's telling you feature 0, which I think was years in residence, less than 15.59. And if that is true, it looks at feature 1, less than or equal to 8.874, which is 8,874. And so if that fails, we go down, passes rather, we go to the left-hand side, and it tells you literally how it arrives upon any root node, any leaf node, and that leaf node's majority label is what that categorization is going to be. Does that make sense? And so for 4-way grouping, for the mortgage application problem, you look at all of those leaf nodes that correspond to approval and all those leaf nodes that correspond to denial. And now you can read off that root to leaf path and actually construct the specific reason with actual values as to why that person was denied the loan. Does that make sense? Any questions? And so a decision tree isn't the only interpretable model. There is a regression version of the decision tree called the regression tree, which applies similar criteria, only how it measures this idea of disorder is not based on information theory, entropy, it's based on variance because it's a real valued label. Does that make sense? Okay, so I've sort of shown you what the result looks like, and we'll continue on with more of the theory on decision trees on Friday. And so please look out, I'll certainly post on the Slack channel about the brain hiccup, about the final project. And please don't hesitate to reach out if you have any questions about the workshop. It is literally just following the video. I wanted to make sure, I was going to post a solution, but I wanted to make sure everyone at least tries it, not just take the solution and hand it back in, as that defeats the purpose of what I was trying to do with Project 6. So I look forward to your submissions, and please don't hesitate to reach out, and I'll see you all on Friday. Yes, question?